I've recently been meaning to read the SmolLM2 paper because I've been using the SmolLM2 135 million parameter model, and I thought I would try a new kind of video for me, which is reading a paper, I guess live, while recording, and I'll be, annotating it in terms of highlighting things. And I also have a Claude project set up, providing it the PDF so I can ask it questions. So let's see how this goes, and we'll jump right in. So the title is SmolLM2, When Small Goes Big, Data-Centric Training of a Small Language Model. Let's see. The largeness of LLMs makes them expensive and challenging, and they document the development in this paper of a 1.7 billion parameter language model. They overtrain SmolLM2 on 11 trillion tokens using multi-stage training process that mixes web text with specialized math, code, and instruction following data. They introduce new data sets, Fine Math, Stack, EDU, and Smalltalk, at stages where we found existing data sets to be problematically small or low quality. They run ablations, and they do a manual refinement process that updates the dataset mixing rates at each stage based on the performance at the previous stage. So that's definitely something that we'll have to understand more. They outperform Qwen 2.5, 1.5 billion, and Llama 3.2, 1 billion, and they release it as well as the datasets. Okay, cool. So, love anything that's related to small language models. Definitely of my interest, both in terms of being GPU poor and also just having the accessibility for it in terms of experiments. Obviously, even though it's small, 11 trillion tokens is not accessible for us GPU poor folks to do. Okay, so we'll go through the introduction, and they talk about language models. They talk about how they're large, more than 10 billion, and a flurry of recent work to produce performance small language models, computationally inexpensive, and can be run on a wide range of devices, and satisfactory performance on many important tasks. The data is a key factor. Data curation has an especially outsized influence for smaller models, as their limited capacity must be carefully optimized for learning core knowledge and fundamental capabilities rather than memorizing incidental facts. Language models are primarily trained on text from the web with sophisticated filtering and processing stages. Specialized data is included, like software and mathematics, or software code and mathematics. And that not only improves performance, but also more generally on challenging tasks that require reasoning. So that's something, yeah, I would assume, I think it was this year, or I guess last year, To Code or Not to Code, exploring impact of coding. Let's give that a look. Including code in the pre-training data mixture, even for models not specifically designed for code, has become a common practice. While there has been anecdotal consensus that code data plays a vital role in general performance, there's only limited work analyzing this. They investigate the impact of code data. Let's see, we find a consistent result that code is a critical building block for generalization far beyond coding tasks, and improvements to code quality have an outsized impact across all tasks. The addition of code results in up to a relative increase of 8.2% in natural language reasoning, world knowledge, generative win rates, and a 12x boost in code performance. Investments in code quality and preserving code during pre-training have positive impacts. Cool. So obviously that's just the abstract, but just take a peek at that. Okay, so they evaluate existing data sets and they do this multi-stage manual rebalancing. So that's not, again, just a recurring concept that I want to understand. And 1 to the 23 flops or $250,000 of GPU compute, which is still, crazy big, but not, relatively speaking, not expensive. They also do an instruction tune variant, and they create new data sets. And these things are state of the art. Okay, cool. They talk about pre-training. Let's see. They again mention how we filter and reformat web text, avoid detrimental repetition in our data sets. Again, this piece about code, improving reasoning and world knowledge. After pre-training, language models typically undergo 2 additional training stages: instruction tuning and preference learning. Instruction tuning is supervised training on pairs, instruction response pairs, on how it should answer a query. Preference learning is about alignment between helpful and unhelpful responses, and that involves reinforcement learning on human-labeled or synthetically generated preference data. Cool. So nice background. Small LMs are more sensitive to noise in the training data. So I think that's worth a quick peek. Oh, I see. So 5.3 mini. Let's see if we can find a keyword hit on sensitive. Not that one. Okay, so it's not immediately jumping out. Let's see, these are references. Okay, well, I don't want to read this whole thing. The model simply does not have the capacity to store too much factual knowledge, but that's not about sensitivity. Yeah, I think I'm going to let this one go. And we'll go back here. Noise. Okay, yeah, sensitivity to noise and training data. Okay, so in addition, designing a pre-training strategy involves selecting and curating data, determining how much to mix from different sources, and so they do a careful evaluation. And when needed, they can create new data sets. Okay, we trained models on each dataset under identical conditions: model configuration, training hyperparameters, and token count. We trained 1.7 billion parameter transformers based on the Llama architecture with a sequence length of 2048, a global batch size of approximately 2 million tokens, the GPT-2 tokenizer and a cosine learning rate schedule with a learning rate of 3 times 10 to the negative 4. So this is the 1.7 billion. So I'm not sure how pre-training learning rates transfer or translate to fine-tuning, or especially with like PEFT. So one thing I'm curious about is like, how does this number translate? If I want to train it with LoRa, should I use this learning rate? I don't know. I'm not really sure what the best practice is on that. They train for the ablations, they trained the model on 350 billion tokens randomly sampled. They use light eval, and here are the benchmarks. Math and code capabilities typically emerge only after extensive training. So when they evaluate that, we started from a mid-training checkpoint at 3 trillion tokens, which was trained primarily on web data. Then we use an annealing approach. The learning rate linearly decays to 0 while training on a mixture that includes the dataset under evaluation. We then used an annealing approach. The learning rate linearly decays to 0 while training on a mixture. So dataset under evaluation. So let's see if Claude can. So can you explain the following statement from 3.1 ablation setup? They took a mid-training checkpoint and they continued training while gradually reducing the learning rate until it reached 0. Okay, so yeah, that is how I understood it. Yeah, we'll get into these other things, but yeah, so that's interesting. I don't quite understand why you would go to 0. I guess that's like stopping training so it evaluates. For math, we annealed on a mixture of 60 billion tokens of the dataset under evaluation and 40 billion from the pre-checkpoint mixture. And then they did this for code. Let's just see. Why do you think they annealed the learning rate to 0? The model makes increasingly smaller updates. This helps model to converge to a stable point in the parameter space, avoiding catastrophic forgetting, fair comparison between datasets using a consistent annealing schedule, meaningful. Yeah, I don't know. Okay, yeah, I'm not really sure if I understand why that's the case. We start from a mid-training checkpoint. We then use an annealing approach while training on a mixture. Oh, okay. So I think I kind of understand it. So because math and code capabilities emerge after extensive training, they start with a somewhat generally knowledgeable model, and then they train on a mixture that includes the data set, like 60 billion tokens for math and 40 billion from the pre-checkpoint. So they're essentially, like, I guess, fine-tuning on this domain before they evaluate. I guess that's my takeaway from that. All right, then they talk about English web data. 2 prominent examples of open data sets that use classifier-based filtering are FineWeb EDU. FineWeb EDU has 1.3 trillion tokens that were deemed educational by a classifier trained on annotations generated by Llama 3 70 billion instruct. Then they use DCLM that was filtered using fast text trained on OpenHermes 2.5, high scoring posts from Reddit, training ablation models on 350 billion tokens each from FineWeb, EDU, and DCLM attained performance shown in Table 1. So if we go up to Table 1, here's FineWeb, EDU, DCLM, and then 40-60, 60-40 to note the FineWeb, EDU, DCLM ratio. And then here's the performance on the task. And it seems like my interpretation of this is that splits are not as effective, I guess, unless for OpenWeb QA. Otherwise, just having one data set gives better performance. I guess that's my takeaway there. It nearly matches FineWeb EDU's performance on MMLU after testing. Oh, I see. Okay, so they're saying it's still close, and at least I guess in this case it does exceed it. So in this case it exceeds FineWeb EDU, so does this, and then it's very comparable there, somewhat comparable there. Whoops, somewhat comparable there. Okay, combining these data sets yields 5.1 trillion tokens of English text. All right, so that's their web data. Then they have math data, and combines recent research has shown that carefully curated mathematical content from Common Crawl combined with targeted filtering techniques can significantly enhance language models' mathematical reasoning capabilities. Yeah, I think nothing more to be said about that. So then they compare two leading publicly available math data sets, OpenWebMath and InfiniMM WebMath. OpenWebMath consists of 12 billion tokens built by filtering math-specific content from Common Crawl, specialized text extraction pipeline to preserve formatting and equations. InfiniMM WebMath is 40 billion tokens, so three-ish times larger, and it matches the performance of the private data set of DeepSeek Math. We performed annealing ablations, so they did that kind of mid-training checkpoint training on a dataset split while going to a learning rate of 0. InfiniMM WebMath achieves a peak accuracy of 14% compared to OpenWebMath's 10%. OpenWebMath outperforms Infi. I've been saying Infini, but it's just Infi. On math. Full evals are here. Despite training on 60 billion math tokens, 5 epochs or 1.5 epochs, performance still lagged behind proprietary state-of-the-art models. Further analysis highlighted two key limitations: insufficient data sizes and insufficient focus on step-by-step mathematical reasoning, along with an overrepresentation of academic papers that focus on advanced concepts. Interesting. Okay, this is more kind of interesting because it's a new data set that I want to try out. The aforementioned issues motivated us to develop FineMath, up to 54 billion tokens of math data focusing on mathematical deduction and reasoning through classifier-based filtering. They extracted text from Common Crawl WARC files using Rosilla Parse, focusing on all 5.8 billion unique URLs from the FineWeb dataset, and then they filtered it with a prompt. So let's take a peek at the prompt. They use it to generate the Silver 3-scale annotations for FineMath. Evaluate the following text extract for its potential usefulness for studying mathematics up to high school and early undergraduate levels. Use the following 3-point scoring system described below. So add 1 point if the extract contains some mathematical content, even if it's not very useful for studying or is an academic paper that is too advanced. So I think that's kind of handling the one of the previous issues. Add another point if it demonstrates logical reasoning in a mathematical context. A third point if it's at the appropriate level and contains clear deductions, step-by-step solutions, ignore formatting errors or missing equations, and make assumptions based on the overall content. The text extract, and then after examining the extract, briefly justify your total score, conclude with the score format, final score, total points. So that's 3 scale. So and they kind of go over what we just saw. We identified domains containing at least 10 pages with a quality score of 2 or higher. And we expanded our domain coverage by including domains with at least 10 URLs from these data sets. So yeah, I'm going to kind of skip over some of that. To retain only high quality math content, we reapplied a classifier trained on Llama 3.1 70 billion instruct annotations using a 5-point scale. And after classification, we performed deduplication to retain only English and applied fast text language classification to retain only English content. Ultimately, we developed multiple variants. So they have Fine Math 4 plus, 10 billion tokens, Fine Math 3 plus, which is 34 billion tokens, and then they have Infi WebMath 4 plus, which is 8.5 billion tokens, and Infi WebMath 3 plus, and we decontaminate each data set against these using 13-gram matching and a minimum overlap ratio with the longest common subsequence of 0.6. So if we take a look at this, and it doesn't look like, yeah, it doesn't look like they have that. Okay. So that one doesn't seem to be posted. All right, moving on to results. Figure 1 presents our Fine Math annealing ablations. Fine Math consistently outperforms the other ones on these benchmarks. Fine Math 4 plus achieves a 2x improvement on GSM-8K and a 6x improvement on math. So that's amazing. This demonstrates the importance of retaining high-quality mathematical content with reasoning. And then Infi WebMath 4 plus outperforms Infi MM WebMath, but plateaus after 80 billion tokens, 10 epochs. Most likely due to data repetition, a trend not seen in Fine Math 4 plus. So that's math data. We move on to code data, and enables diverse use cases such as completion, debugging, software design. General purpose LLMs are increasingly deployed as coding assistants. And then recent research shows that including code data enhances general natural language reasoning and world knowledge. They start with the stack data set, stack v1, StarCoder data, stack v2, StarCoder 2 data, and looks like this is the one they created. FineWeb edu classifier-based filtering strategy can be effective for code data. So we construct stack edu, a filtered variant of StarCoder 2 data, focusing on educational and well-documented code. They select 15 largest programming languages from StarCoder 2 data, and this has 450 billion tokens. Then they train language-specific classifiers using the star encoder model on synthetic annotations generated by Llama 370 billion. So if we look at that prompt, again, they have like a scale, so 5 scale annotations. At one point if the program contains valid Python code, another point if it addresses practical concepts, etc. They do the annealing ablations again. Filtering with a threshold of 3 improved performance across most languages while maintaining sufficient data, although Java performed better with threshold 2. Okay, the resulting stack EDU dataset contains 125 billion tokens across 15 languages. And I'm particularly curious about Python. So they have 22 billion tokens of Python. And I don't think they have published stack EDU. I think they've published they've published the classifier. This is the classifier for scoring the educational value of code files in the Stack v2 dataset. We use this classifier for building Stack EDU, and so yeah, that's the classifier. Okay, let's keep moving. Table 2 shows statistics of the top 4 programming languages. So we already kind of looked at that. All right, next section, pre-training. A clear shift towards longer training durations, especially for smaller models. While this strategy deviates from the chinchilla optimal guidelines, the resulting performance gains and reduced inference costs make extended training a worthwhile trade-off. I've heard of these before. I don't know exactly what they are, so we should probably take a quick look. And let's look at this. Okay. We demonstrate that the transformer models with the same pre-training loss, but different model and data sizes generate the same performance on various downstream tasks. We also discovered that a model exhibits immersion capabilities or abilities on certain tasks, regardless of the continuity of metrics. When its pre-training loss falls below a specific threshold. Am I looking at the right thing? Let's see, what was it? Hoffman. No. I was not looking at the right thing. Okay. Okay. We investigate the optimal model size and number of tokens for training a transformer language model under a given compute budget. We find that for compute optimal training, the model size and number of training tokens should be scaled equally. For every doubling of model size, the number of training tokens should also be doubled. And then they test this hypothesis by training a predicted compute optimal model chinchilla, 4 times more data. Okay, so I think what the SmolLM2 paper is saying is that this doubling of model size, meaning training tokens should be doubled, is not what they're doing. They're doing the opposite, which is that they are training small models for very long token durations or token counts. So 11, I think it was 11 trillion tokens. Qwen2 was 1.5 billion, was trained on 7 trillion tokens. Qwen 2.5, 1.5 billion on 18 trillion tokens. Llama 3, 2.1 or Llama 3.2, 1 billion was trained using distillation on 9 trillion tokens. So SmolLM2 is trained on 11 trillion tokens. Approximately 2 epochs on our collected datasets. And then they had this multi-stage approach, which I'm curious about. Okay, 4 principles: performance-driven interventions. We monitor evaluation metrics on key benchmarks and adapt dataset mixtures to address specific capability bottlenecks. Upsampling high-quality math and code during the annealing phase. Reserving datasets like fine math and parts of Stack EDU for the final stages to maximize their impact. I don't know, I just feel like this is really cool, and I'm curious to, try that out on obviously on a much smaller scale, but it seems like the concept is that the model learns basic grammar and reasoning, or I guess general knowledge, maybe some reasoning, maybe language, or definitely language in the early stages, and then once its capabilities get up to speed, then you give it the more high quality complex data. So that's what I'm guessing. If we look at this one, Blakeney. Okay. In this work, we show how to leverage the smaller domain-specific datasets by upsampling them relative to Common Crawl at the end of training to drive performance improvements on difficult benchmarks. This simple technique allows us to improve up to 6.9, I guess is that points, on MMLU, 8.26 relative to the base data mix. The duration of domain upsampling from 5 to 30% of training, and we find that 10 to 20% is optimal for navigating the trade-off between general language modeling capabilities and targeted benchmarks. We experiment with ablating the duration of domain upsampling from 5 to 30% of training. Okay, so if you were doing a million tokens, then they go, or I guess let's just say 100 tokens, you would go from 5 to 30 tokens. And they find that 10 to 20% is optimal. All right, we're not going to look in too much into that, but I wanted to take a peek. Strategic introduction of medium-sized datasets, introducing them mid-training to avoid dilution by larger datasets early on. Strategic introduction of medium-sized datasets such as OWM, InfyMM, WebMath, and StackEDU mid-training to avoid dilution by larger datasets early on. So that's interesting. So that kind of seems relevant or related to upsampling, but I think this is more about timing. Not sure. Avoiding excessive data repetition. We stay close to the 4 to 5 epoch threshold for most data sets. And yeah. All right, let's take a look. Some decisions were informed by established findings. Others were driven by empirical insights during training. The data mixtures of the 4 pre-training phases. So stage 1, 90% English web, 10% star coder data, StackEDU. Then stage 2, they increase star coder data, StackEDU. They introduce their math data sets. Then they increase math. They decrease code and English web. And then at the final stage, they have textbooks, highest amount of math across the stages. And then they actually increase the code again and the lowest amount of English web, but still dominating. So you still have over 50% of your dataset mixture is English web. And the breakdown is 6 trillion tokens, 2 trillion, 2 trillion, 1 trillion. So this is really interesting. And, something that I should definitely refer back to. Okay. So, where were we? I think we looked at... Oh, okay. We're right here. Okay. Data mixture in figure 2. Okay, great. Training setup. All right, Llama 2. So look at Appendix A. 24 layers. Yeah. So that's just there for reference. We trained the model on 256 H100s using the Nanotron framework. They use AtomW with a warm-up stable decay, learning rate schedule to avoid setting a fixed training duration. And here's the learning rate schedule. Peak learning rate of 5 ENEG 4. And could transition to a decay phase when needed, reducing the learning rate to 0 over 10% of the total training steps. So I think this is that evaluation strategy, I think. Tokenizer from here, which is SmolLM. And it was trained on a mixture of this. Cool. So stage 1, stable phase. So this is mostly English web data. 0 to 6 tokens. So 60% fine web EDU, 40% DCLM, which they showed in that table. And again, this is not Find Math, right? This is Find Web EDU. For code data, we incorporated star coder data consisting of 250 billion tokens across 80 programming languages, limited to 10K, and then they wanted to keep room for upsampling in later stages. We did not include math data because of the size. So I think in order to upsample it, I assume you need to have enough to upsample increasingly. So I think that's why they didn't include it. All right, so after 6 trillion tokens, so here's stage 1, 2, 3, 4. Stage 4 is the best for each count, or sorry, for each benchmark. I don't think anything stands out. Everything, well, I guess this stands out. The generative tasks decrease from stage 1 to stage 2, and then increase again from stage 3 to stage 4. So that's interesting. Okay, let's see. Sorry, I lost my spot. Let's go back here. Okay, we observe poor coding and mathematics performance in stage 1, which makes sense. All right, stable phase, stage 2. They added math at a 5% ratio and increased the proportion of code data, including OWM reflects the small size and our gradual approach to incorporating math content. The final mixture was 75% web data, 20% code data, 5% math data. Code performance improved in stage 2 from 8.8 to 10.6. We observe above random MMLU accuracy with multiple choice formulation. MSF explicitly outputting an option from ABCD, or instead of computing the likelihood of different answers. Okay, stage 3. They add the text-only English portion of InfyMM web math. So math is at 10%. They switch to 4060 for English web data, and they replace star coder data with stack edu. And for languages with fewer than 4 billion tokens, they use star coder 2 data subsets. They also add Jupyter notebooks. Yes, agreed. Rich contextual examples of code interleaved with explanations. That's really interesting. I don't know. Obviously, it's been done before. Let's take a quick peek at that. I don't know if I want to. I think this is the star code. Yeah, I don't think we want to look at that right now. But yeah, interesting that they're using Jupyter notebooks. That would be cool to see more of that. Okay. A noticeable loss spike, which remained even after rewinding training and skipping data associated with the spike. The exact cause remains undetermined, but the most evaluation metrics recovered by the end of the stage. And then they have the decay phase, where they decay the learning rate linearly to 0 for 10% of the total training duration, so 10. Then they introduce their highest quality math data sets, and certain allocations. 14% data was math. They expanded Stack EDU to cover languages not covered in stage 3, which was 24%. We maintained the natural distribution across programming language with a higher allocation for Python and 58% web, with the higher the 60-40 ratio. I guess 40-60 is how they call it. And Cosmopedia at 4%, which provides 30 billion tokens of high quality synthetic textbooks. All benchmark tasks show improvements, substantial gains in coding and math. So if we take a peek, so math doubles more than, or yeah, I guess what is that? Almost doubles. Or sorry, stage 4. So yeah, triples. Math triples. Code goes up 6 points here and then 7 points here. So yeah, half the number of tokens, but higher quality of data. Okay, after this step, we obtain the final SmolLM2 base model. So that's a good reference point. They extend the context length from 2 to 8K tokens by taking an intermediate checkpoint from stage 4 and continuing training with a different data mixture and a rope value of 130K. So that's interesting. This mixture was adjusted to include 40% long context documents from DCLM, FindWeb EDU, and the books subset of DOLMA. So I think that's the textbooks bucket here. And then after the remaining 60% followed the stage 4 mixture. Oh, okay, yeah, never mind. So this is after stage 4. And so after this step, then, so that the base model is after the context length extension. And this was for, hold on, I don't think I'm understanding this correctly. So they took an intermediate checkpoint from stage 4 before the final 75 billion tokens, and then they continue training. So, okay, so I think they train through stage 4, and then they start with a checkpoint that's 75 billion tokens before the 11 trillion tokens, and then do a different data mixture and a different rope value. And I would assume they do it for 75 billion tokens, though I'm not sure. Yeah, so that's interesting. Okay, so base model evaluation. Table 4. So I think it's this one. And SmolLM2 is leading the way, except for natural questions. GSM-8K, math, human eval. Wow, that's amazing. Quen 2.5. Wow. So double, triple on math, and almost double. So anyways, that's pretty impressive. If we look at the ones where SmolLM2 is leading, I don't see that big of a jump. I guess MMLU Pro is pretty big, almost double Llama 3.2. That's interesting. I mean, that's very significant. So is this. So yeah, that's interesting. Okay. All right. Let's see. 6 percentage points on MMLU Pro, further validating its generalization capabilities. Competitive on math and coding. Outperforms Llama 2 or Llama 3.2 on GSM-8K math and human eval. We see next to no degradation in performance after context length extension in Appendix G. Cool. All right, so that's base model. After training the base model, we do post-training through instruction tuning and preference learning. For post-training, we leverage existing datasets in addition to a new instruction tuning dataset called Smalltalk. Smalltalk is a dataset that combines selected existing datasets with new synthetic datasets, including the Magpie Ultra conversational dataset and these other ones. All datasets were generated using Distillable. Magpie Ultra is a multi-turn dataset. Right, I'm just gonna speed up the reading a little bit here. They filtered it. We developed additional task-specific datasets to further enhance model instruction following with detailed constraints, summarization, and rewriting. Small constraint contains 36,000 instructions with detailed constraints similar to the one found in IF eval. And they have this. So here's Smalltalk. 1.1 million rows, and here's the breakdown. So here's the small constraints. Your entire response should be in English, lowercase letters, no capital letters. The word the should appear 5 times, should contain 3 bullet points, etc., etc. So that's really interesting. take a peek at rewrite. Rewrite the input text to make it more concise while preserving its core meaning. Okay. OSS instruct. Write a Python function that computes the maximum volume. Da, da, da. Okay, interesting. So yeah, that's Smalltalk. Okay, they generate instructions using 72 billion, Quen 2.5 instruct, filtered out conflicting constraints or incorrect responses, so 56.3 instruction response pairs. Again, 72 billion to summarize and rewrite the given text for 1 million summaries and 600,000 rewritten texts. Cool. Let's see. To improve mathematical reasoning, we evaluated public math instruction datasets by fine-tuning on mixtures with 80% general instruction data and 20% math data from various sources. Results in Table 10 highlight complementary dataset strengths. Numina Math, COT, was strong on math and empty bench. MetaMath QA, which was also included in OpenHermes 2.5, improved results on GSM-8K. Based on these findings, we incorporated a combination of both datasets in Smalltalk, so that's good to know. If we look at Appendix F, composition of Smalltalk. So new datasets are these ones. Here's math data, and then here's other, so good to know. Yeah, I'm particularly curious about these two in terms of fine-tuning this more, so good to know that they're already using this in SmolLM2. Although this is the instruction, so this is not in the base model. So base model is, I guess, free of not contaminated with this dataset, these datasets. Okay, code generation, 50,000 pairs of instruction response for Python. System prompts, 30,000 randomly selected samples, 80,000 samples for function calling. Long align, 3.7 samples with 8 to 16,000 tokens. Okay, and they kind of go here. We found that incorporating these datasets with a specified number of samples effectively enhanced their target capabilities while preserving strong performance across other benchmarks. This is the comparison of instruction tune models. SmolLM2 1.7 billion instruct exhibits strong performance in instruction following, reasoning, and math. So again, Quen 2.5 is strong here. What else stands out? This is again MMLU Pro is strong relative to Llama. Yeah. Okay, we already saw Appendix F. We performed supervised fine-tuning for our base model for 2 epochs using a global batch size of 128, sequence length of 8,192, and a learning rate of 3 times 10 to the negative 4. So that's helpful to know that that's their fine-tuning learning rate. They use DPO on various public synthetic feedback datasets, and they improve these benchmarks using by using ultra feedback. Interesting that they have a smaller learning rate for that. After this final stage of DPO training, we obtained the instruct SmolLM2 model. Short context data did not impact the model's 8K context ability. Okay. So we already looked at the comparisons. So SmolLM2's ability to generalize, capable chat assistant, and then here's what I'm interested in, is the 135 million one, and I guess eventually the 360 million one. 4 trillion for 360 million and 2 trillion for 135 million. I think this was the same number of tokens for modern BERT, which I think is a similar size. We reran data ablations at the target training length to determine the most effective data mixture. We found that filtering DCLM with the FineWeb EDU classifier, removing samples with score 0, and downsampling those with scores 1 and 2 work best. Unlike 1.7 billion, where we leveraged a multi-stage training strategy, these smaller models benefited from a single-stage training approach with consistently high-quality data. So that's definitely interesting to note. So I guess what I was talking about earlier of using that, getting familiar with that 4-stage might not apply for smaller models. StackEDU, InfyMM WebMath, FineMath, and Cosmopedia from the start. They use grouped query attention, and learning rate is 10 times larger. They use a filtered version for instruction tuning. They remove complex instruction following tasks and hard samples. They do DPO on ultra feedback and respective model cards. So yeah, those are on Hugging Face. Okay, and we're at the conclusion. Our approach highlights the critical role of high-quality specialized datasets in enabling smaller models to achieve strong performance across a variety of benchmarks. The development of FineMath, StackEDU, and Smalltalk address limitations in existing public datasets, improving capabilities in reasoning, mathematics, and instruction following tasks. To support future research and development, we release SmolLM2 alongside the datasets and code used in its training. These resources provide a comprehensive foundation for training performant small language models, making them accessible to a broader range of researchers and applications. So that is awesome. We can take a quick peek at the appendix. I don't think I'm going to go into it too much detail. We already saw some of these things. Evaluation curves of ablation models trained on DCLM, FineWeb EDU, and their mix for 350 billion tokens. And here's the 60-40 split in red. And it clears DCLM in some of them. It clears FineWeb EDU in some of them. Here are the FineMath ablation models trained on OWM and InfyMM WebMath. We saw some of these prompts. We saw this breakdown. Pre-training results. Here's the full set. This is interesting. The progression of MMLU scores throughout the stable phase, so up to 10 trillion. And I think it's called stable because of the learning rate is stable. I think that's why it's called stable. Let's check, why are some stages of training called stable phases? Yeah, learning rate remains at its peak value without decaying. And this is contrast instruction tuned performance, needle in a haystack, evaluation. I'm not familiar with this. Yeah, not 100% sure on that. Helmet benchmark, that's interesting. What is the helmet benchmark? It is how to evaluate long context models effectively and thoroughly. 7 diverse categories of tasks. So they have, oh, I see, so they have some RAG, re-ranking, Q&A, summarization. Interesting. Okay. Cool. So yeah, I think I'm gonna go back up. I think I'll call that for this video. Again, first time I'm trying something out like this, so it's probably a bit clunky. But yeah, I'll probably be doing this more because I want to make more videos and I want to read more papers. And so this is a good way to do both. So yeah, definitely be on the lookout for more videos where I'm reading papers live. I didn't use Claude as much. I usually use Claude a lot more. Multiple chats, screenshots, analysis, looking things up. I think this paper was, more straightforward than other papers are, so that was really awesome, and it was a pretty good read. And so definitely excited about continuing to use the SmolLM2 models. And yeah, we'll see you in the next video. Thanks.